So calculating the pH of a weak acid solution. So to answer this kind of question, you don't really have ever need to have seen the weak acid before in your life. So don't get put off if you see something like aloxanic acid, right? What is that? Who knows? I don't know, right? The clue is for the formula of an inorganic acid, it's often written in the form HA, where H is going to be the proton that's ionizable and A is going to be whatever anion is going to be left after the acid has donated its proton. So my generic weak acid plus water is going to give my conjugate base. So whatever is left of the rest of the acid after it's donated at H plus, it forms its conjugate base and the hydronium ion. And we can base our Ka expression for literally any weak acid ionization on this generic form. So Ka is going to be of the form of the concentration, the conjugate base times the concentration of hydronium at equilibrium divided by the concentration of the weak acid. So let's go ahead and do it with this aloxanic acid, HC4H3N2O5. So that will donate a proton to the water, and we will end up forming its conjugate base. So what do we have after we've lost a proton? We're just going to have the C4H3N2O5 minus anion. So probably the aloxate anion. I don't know. It probably has a name. Do we need to know it? No, we do not. And we'll leave it at that. So now I have my equilibrium written out. I can go ahead and use an ice table to put in the information I know and the information I don't know. So I'm going to start with my concentration of my weak acid, whatever that may shake out to be. My concentration of my conjugate base, N2O5 minus, my concentration of hydronium. So with these kind of questions, you should always be able to fill out the top row because you can given the initial concentration of the weak acid, and you're going to assume that if nothing has ionized yet, then you're going to have a concentration of 0 of your conjugate base and approximately 0 for your hydronium ion. Of course, autoionization of water means there's some, but it's going to be negligible. So we're told the solution concentration of the aloxanic acid is 2.4 molarity. So we can just stick that in, 0 for the conjugate base, 0 for the hydronium ion. So we're going to need a change row and our equilibrium row. So the easiest thing to do is say, well, equilibrium, I want to solve for the concentration of hydronium, so I'm going to make that X, okay? So what has to change in order to get from these initial concentrations to the equilibrium concentrations? Well, we are going to form X amount of the hydronium ion. Looking at the balanced chemical equation, simultaneously, we're also going to form X moles of our conjugate base, which means our equation is traveling to the right, from reactants to products, which means we are going to give up, ionize the same number of moles of our weak acid to form X moles of conjugate base and X moles of hydronium ion. So the change in the concentration of our weak acid is going to be minus X. So to work out our other equilibrium concentrations in terms of X, we're just going to add down each column. So initial plus change equals equilibrium. So the equilibrium concentration of our weak acid is going to be 2.4 minus X. Our equilibrium concentration of our conjugate base is going to be X. And now we just have our equilibrium concentrations in terms of X. We can substitute those into our equilibrium constant expression. So that's going to take the form of the concentration of our conjugate base, N2O5 minus, times the concentration of hydronium at equilibrium divided by the concentration of our weak acid at equilibrium, N2O5. And because we've been given the equilibrium constant, Ka, well, that's just going to be equal to some number. In this case, Ka is 2.24 times 10 to the power of minus 7, okay? So now we can just substitute in those equilibrium concentrations in terms of X that we just worked out, and we can rearrange and solve for X. When we have X, we have our concentration of hydronium at equilibrium. Easy, right? So let's substitute those numbers in. So our equilibrium concentration of our conjugate base is X, and of our hydronium is X, and then our equilibrium concentration of our weak acid is 2.4 minus X, and that is going to equal our equilibrium constant, Ka. And of course, that is going to be equal to our Ka value of 2.24 times 10 to the power of -7. So that then becomes a fairly simple mathematical rearrange and solve for x. You're going to end up with a quadratic of the form like ax squared plus bx plus c equals 0, okay? However, we can make this even easier for ourselves 99 times out of 100 because if you think about it, we are usually dealing with pretty dilute solutions where the concentration of hydronium is going to be a lot less than 1, quite often like of the order of magnitude 10 to the power of -3 or even smaller. So if you compare that order of magnitude of x to the number it's being subtracted from, just imagine that 2.4 minus x, imagine the x was 0.0001, right? Not hard to imagine. That 2.4 to 3 significant figures is going to be unaffected by subtracting 0.0001 from it, right? It's still essentially going to be 2.4. So we're going to do what's called the x is small approximation, which is going to be your friend for getting through these problems really speedily. If we assume x is small, we can get rid of that minus x. And then this rearranging and solving for x gets really easy because we just have x squared on the top divided by, oh, I shouldn't put capital X there, divided by 2.4 equals a number, 2.24 times 10 to the power of -7. And that's a very easy rearrange and solve. The one caveat, though, is that we do have to go ahead and check that the x is small approximation is valid when we finish, which usually means checking that there's less than 5% ionization of our acid. So taking whatever number we get for x divided by the initial concentration of our weak acid and times by 100 to work out what that is as a percentage. Okay, so then we're going to end up with x squared equals this 2.24 times 10 to the power of -7 times 2.4. That's just going to be a number, right? So then we can just take the root of that. So x is whatever the square root of that number is going to be. I don't have a good way of drawing a square root on here. I'm going to have to freestyle it. Times 2.4. Let's go ahead and draw that. See how ugly I can make this look. So here's my square rooting of all this stuff. So now I'm going to end up with a number for x, which is, again, is much easier than solving the quadratic because you just get one value for x rather than solving the quadratic gives you two values and then you have to decide which one's the good one, right? Which one's valid. So I end up with x is 7.33 times 10 to the power of -4. So again, my experience tells me looking at that, 10 to the power of -4, that's many orders of magnitude difference between that and my value of 2.4. But I'm going to go ahead and check my x is small is valid before I continue. So I'm going to take, that is not how one spells check. I'm going to take my value of x and divide it by my initial concentration of my HA, my weak acid. So that in this case, that's going to be the 2.4 and times 100 to convert that to a percentage. And what I'm looking for is if it's less than about 5%. So my value of x I got was 7.33 times 10 to the power of -4. Divide that by that 2.4 that it was being subtracted from to make sure that it is indeed small enough that to the number of sig figs we're working with, it doesn't matter. And I get a value of 0.03%. So definitely x is small is valid. So I was right to save myself a lot of bother and go ahead and do that. So the last thing is we have a value for x. X represents the concentration of my hydronium ion at equilibrium. And I've been asked to calculate pH. So without further ado, don't forget to, actually finish the question. pH is minus log of the concentration of hydronium at equilibrium. So stick that in your calculator. Drum roll, please. Minus log of, what was it, 7.33 times 10 to the power of -4 is what we solved. And I get a value for pH of about let's see, one decimal place, 3.1, which sounds like a reasonable pH for the ionization of a weak acid. And that's all there is to it. And honestly, these questions, the more of them you do, you're going to find they're very similar. The only thing that is really going to change is the initial concentration of your weak acid. So this part is going to change. So you're going to usually end up with an answer of the form, if x is small is valid, you're going to end up with x squared over whatever the concentration of the weak acid was, and that is going to be equal to whatever your Ka is, and you're just going to rearrange and solve that for X. That's really what you're going to be doing the majority of the time with these kind of questions. So hopefully that helps you finally crack calculating the pH of a weak acid solution.